These atolls are these ring-shaped islands that surround a central lagoon. And being very narrow pieces of land, that means that they don't take up a whole lot of surface area. The entire nation encompasses just 70 square miles. But those 70 square miles of land are stretched over thousands of square miles of ocean. So as Marshalese people like to say, they are not a small island nation. Instead, they are a big ocean nation. And being a big ocean nation, or living in a big ocean nation, the Marshall Islanders have to have creative ways of navigating the ocean. And this is one of the reasons I was excited about working in the Marshalls in the first place. Back in high school, I visited an art museum in Boston, and tucked away in the basement was this Marshalese stick chart. This is a chart that the Marshalese traditional navigators can use to navigate between islands. And those islands are represented by these cowrie shells here. And they're connected by sticks made of coconut fronds. And those sticks mark patterns of ocean waves. When the trade winds blow, they generate these waves called ocean swells. And those ocean swells can bend around or bounce off of the islands in complex ways. But the Marshalese have memorized and understood these wave patterns. And so they could navigate from island to island, hundreds of miles, just by feeling the direction of these waves with the hull of their canoes. So this chart really illustrated to me that the Marshall Islands is home to a culture in which the land, the sea, and the sky are all intimately connected. And this isn't true just for the culture of the Marshall Islands, it's also true for its climate. The climate of the Marshall Islands is intimately connected to the world around it, because it sits at the heart of Earth's tropical rain belt. And here in this very washed out graph, you can see the tropical rain belt right here in blue. So the rain belt is formed when the trade winds from the northern and southern hemispheres converge, hence our convergence zone. And they warm this tropical sun and they rise. And this rising motion generates a lot of convection and a lot of rainfall, which is why this area is Earth's rain belt. This rain belt encircles the globe, and it shifts northward and southward through the seasons. So, for example, during the summer, the northern hemisphere warms, and that pulls the ITCZ northward. Conversely, when it's winter in the northern hemisphere, the ITCZ is pulled southward as the northern hemisphere is cooler. And so this dictates the seasons of wet and dryness in the Marshall Islands. But it's important to recognize that the intertropical convergence zone isn't just important to the Marshall Islanders, but to the rest of the world as well. Because we can kind of think of the ITCZ as being at the heart of Earth's climate engine. Because this is where all this energy that's created in the tropics gets distributed towards the poles. When that rises, it eventually diverges and moves poleward. And as it does, it loses its moisture, it dries out, and eventually subsides again. And it does this at about 30 degrees north or southward of the equator. So does anybody know what latitude we are here in Tucson? Just shout it out. Yeah, 32 degrees north. So we are basically right underneath this area of subsiding air, and because it's so dry, it's the reason that you find the desert here, and you find most of the world's deserts at 30 degrees northward or southward. So what happens in the Marshall Islands doesn't stay there, because it's connected to the rest of the world via this circulation cell that redistributes energy from the equator towards the poles. But this isn't the only way that the tropical rain belt impacts the Marshall Islands. There are other climate impacts as well. And probably the most obvious of these is sea level. Because the Marshall Islands sit on average just 6 feet above sea level, about as high as I am. And as you probably know, sea level is rising. So this is a graph I made. On the right hand, we see the amount of sea level rise in inches, and here it's in centimeters, if that floats your boat. And it floats your boat. But it plots the sea level rise between 1880 and today. And as you can see, sea level has risen by a little less than a foot, or to put it in another sense, about 1.5 bananas. So 1.5 bananas, or 1 foot, doesn't really sound like a whole lot, especially not stretched over 100 years. But it makes a big difference when you're living just 6 feet above sea level. When you're just 6 feet above sea level, every inch matters. And so this means that the Marshall Islands are incredibly vulnerable to rising seas. And that sea level rise is fundamentally linked to the supply of fresh water in the Marshall Islands. Because we're already starting to see some of these climate impacts. The islands are flooding on an almost regular basis now. And when the islands flood, it brings seawater onto the land. And that seawater can infiltrate into the groundwater supply of these islands. That makes the water salty and undrinkable. So that means that islanders, rather than relying on groundwater, which is more reliable to meet their freshwater needs, they instead have to rely on rainfall to meet their freshwater needs. But patterns of rainfall are changing in the Marshall Islands. Over the past 50 years, so between 1950 and 2011, the amount of rainfall in the Marshall Islands decreased, and this gave rise to unprecedented droughts in the Marshall Islands. For example, in 2016, the intertropical convergence zone shifted towards the equator, away from the Marshall Islands, leaving them high and dry. And this led them to declare a national emergency, as their crops failed and there were disease outbreaks. So ultimately, this sets a pretty firm timeline for the Marshall Islands. Without drastic interventions, this means that the Marshall Islands could be uninhabitable as early as 2040, as their freshwater supplies dwindle. So what this means is that we really need to understand the rain belt, because it's what dictates the freshwater supplies to the Marshall Islands, and thus its habitability over the next few decades. So we need to understand how the position of the tropical rain belt has changed through time. We can do this using satellite data. Satellites can remotely sense the amount of rainfall falling in a given area, and this is great in remote regions like the Marshall Islands where there aren't a whole lot of rain gauges to measure. And so we can plot. This is a terrible figure. Okay. Well, you can pretend that there are seasonal cycles here in the ITCZ through time, and so we've plotted it from 1980 over to 2020. And so that gives us 40 years of data, and as you can see, even with this terrible projector, that the ITCZ shows no trends. It's not moving northward or southward. But that doesn't mean there aren't any, it just means that we only have 40 years worth of data to measure them. And on the climate scale, that's just too short. We need more data. So this raises a bigger question. How can we learn what the climate was like before we have observations? This is where corals come into play. Corals are animals, a lot like jellyfish, and they grow as these tiny. So these polyps live together, they feed together, and they grow together. And they form these skeletons made of calcium carbonate as they grow. As they stretch towards the sunlight, they form these layers, which you can't see here, but pretend there are layers, that grow upwards through time. And so these layers contain chemical signatures of the climate that they formed in. And so by measuring the chemistry of these layers of the coral skeleton, we can track changes in climate through time. So my goal with this project is simply to use these Marshall Islands corals to reconstruct the history of the tropical rain belt through time, and thus extend our instrumental record. So in 2016, that's exactly what we did. We wanted to establish some groundwork for our research. And so we wanted to answer 3 questions. The first off is, what is the climate like in the Marshall Islands? How much does the climate at these coral sites reflect the climate of the broader ocean? Second of all, what is the chemistry of the seawater in these areas? And how does that seawater change seasonally? Because we can use that chemistry of the seawater to study how the corals respond to that changing chemistry of the oceans. And then finally, are there corals here that we can use to reconstruct past climates? So to do this, I donned my scuba gear and our whole team went diving. And so we dove at several sites around the Marshall Islands at 2 atolls, both the main atoll, Marshalese, and a more isolated one a few hours to the east, Arno. And our goals were to, number 1, measure the conditions of the ocean. And so we collected seawater samples that we then brought back to the lab to measure their chemistry. We also placed a series of temperature loggers at key coral sites around both atolls. And these temperature loggers are little instruments about the length of my hand that are encased in PVC tubing and then zip tied to the undersides of these coral reefs. And the idea is that we can come back in the future, collect these loggers, and then see how the temperature has changed seasonally, and then use that to understand the climate conditions that these corals are growing in. our second task was to actually find these corals. And so, not all corals are created equally for climate purposes. Okay, thank you. Cool. Not all corals are created equally. We don't like the small, kind of branching, hand-shaped corals because although they're pretty fragile as well, and they're also difficult to sample. And both of these factors make them less desirable for us to core. Compare that to these big, blocky, bulbous corals like this one here. They're nondescript to look at. It's really hard to draw them, but they are incredibly useful for climate purposes because they can be very long-lived. And because they're easy to sample. And so we measured a bunch of parameters with these corals. Our goals were to find as many corals as possible, and then measure the seawater depth and their location so we could go back in the future and find and drill these corals. And then, our observations about the corals. How healthy are they? In addition, how drillable are they? A core that has a whole bunch of wormholes, literal worms drilling holes in the coral, is going to be very difficult to get a skeletal sample of. So we want to know how healthy and intact the coral is. And finally, how big the coral is. And we're going to probably have to pause here for a second. Train break. Okay, cool. So we want to know how big the corals are. And so we obviously photograph these corals when we're down there diving, but just looking at a photo of the coral without me at the top, you couldn't tell how big the coral is. You'd need a sense of scale. It's really hard to dive with yardsticks, so we didn't even try. Instead, we quickly realized that my fingertips stretch apart like this. They're exactly 6 feet, fingertip to fingertip. So I was the scale bar. So there are hundreds of pictures of me stretched out into these weird Jesus poses, or these Superman poses. But it works. You can tell how big these corals are. Like this one is roughly 6 feet tall. Woohoo! Yeah. And why do we care about the size of these corals though? It's because the bigger the coral is, the older the coral is. So a coral that's about as tall as I am, if it's growing at about 2 centimeters a year, it means it could be roughly 100 years old. So keep in mind that our instrumental record from satellites is only about 40 years long. So with one coral that lives 100 years, we can more than double the length of our instrumental record. Of course, our corals don't need to be alive to do this because we're only interested in the coral skeletons. So we hunted for dead corals as well. And we call these fossil corals only because we don't know how old they are. They could be decades old, they could be centuries or millennia old, but they died before we found them. And we find their skeletons all around these islands. We find their skeletons everywhere. And in the meantime, our PI of our lab, the leader of our lab, Diane, she could not dive for medical reasons for the first half of this trip. She was stuck on land, and she made excellent use of that time by searching around these islands looking for fossil corals. And she came back one day with this look on her face, and it immediately told us that she had succeeded. And so she'd found literally dozens or hundreds of these coral cores scattered all around the islands, and which is incredible because if some died decades ago and some died centuries or millennia ago, that gives us windows of time over the lifetime of each coral that helps us reconstruct changes in climate over really long time scales. So it's an incredibly valuable resource to have, these dead corals. And so for each of these dead corals, we chiseled off a small sample of their skeletons. And you can see what looks like what looks like an innocuous gray boulder on the outside is actually a coral on the inside. And you can see this when you chisel away the outer surface of the skeleton and reveal this pristine skeleton inside. And so we took samples of this pristine skeleton inside and brought them back to the lab. Our question is whether or not these corals were suitable to use for climate. And to do that, we look at these corals under a microscope. This is done with a scanning electron microscope, incredibly high magnification, and we examine the coral structures, this coral skeletal structures. And we want to know if, when that coral has been sitting out for decades or centuries or millennia, if it's changed at all, if some of the skeleton has eroded away, or if new material has kind of filled in the gaps in between. And both of those can impact the chemistry that we'll eventually measure in these coral skeletons. This coral didn't make the cut. This coral looks a little bit fuzzy, I don't know if you can tell, but it has a kind of grainy texture on the surface, which tells us that there are new crystals that have formed, tells us that the chemistry has been altered. But this gave us a tool to identify which corals we could use for climate and which ones we couldn't. And so we went back to the Marshall Islands in 2018, armed with this knowledge of which corals we were going to sample. And that's what we did. But we did this in January of 2018. And January is the windy season in the Marshall Islands. It's incredibly windy, it's incredibly wavy, which means you're not diving in those conditions. So we were restrained to land, which is not a bad thing when you're hunting fossil corals, which are on land. And they could have been brought there by a variety of climate processes, like natural processes, like tsunamis, cyclones, things like that, or human processes. I'm talking about things like dredging, where they physically bring the corals ashore. But for whatever reason, these corals find their way onto the islands, where we can sample them. And that is exactly what we did. Yeah, so here we are standing on the coral you saw earlier. So this coral is standing on its head. It's inverted. So Diane is standing on its base, and the youngest portion of the skeleton is buried in the sand. And we bring this gas-powered drill out into the field that's fitted with a drill bit about this big in diameter, put it right on the base of the coral, and drill all the way down. And that gives us a coral skeleton core about this big around, stretching the full length of the coral, from the oldest to the youngest parts. And after we collect these coral cores, they went on a wild journey. So one of the more interesting aspects of science is that it's inherently collaborative, and your collaborators can be all around the globe. So if you want to analyze a coral, sometimes you need to go all around the world. So these coral cores started off in the Marshall Islands, and they went back with us to our lab, which at the time was at Boston University. And there we did some initial data analyses on these cores, we cleaned them, and we drilled small samples from their skeletons, which we then brought across the river over to MIT. Oh, this is way behind. That is not the right direction. There we go, MIT. And there at MIT, we dated these corals. We had to figure out how old they were. And we do this with a process that's kind of similar to carbon dating without the carbon. We measure the ratios of certain isotopes, uranium and thorium, that change through time, and that gives us a really good metric for how old a coral is. We found corals that had died maybe a few decades ago, as recently as the late 1990s. We found corals that had died 5,000 years ago. So there's an incredible range of ages of these corals. And armed with that knowledge, we brought these corals over to the Australian Institute of Marine Science. And there we worked with collaborators to mount each coral core inside this metal tray, which then we mounted onto a computerized saw. This saw is programmed to slice your coral at very precise intervals, something like 6.5 millimeters per slice. And then we clean those slices and x-ray them, and that's what you're seeing on the right here. And that reveals the layers of growth inside. Finally, we brought these corals to the University of Arizona. And here, we're measuring coral skeletal chemistry. What do I mean by that? Well, we can picture a simplified version here. We've got a coral that obviously grows in seawater. And seawater, like all water, is composed of H2O, hydrogen and oxygen. And that oxygen can come in a couple different flavors, 16 and oxygen 18. One of them is a little bit heavier than the other. The oxygen 18 is a little bit heavier, which makes it behave in slightly different ways. For example, when water evaporates in hot and dry conditions, the water that evaporates tends to have a lot more oxygen 16. And so that leaves the seawater that's behind with more oxygen 18 in it. And so the coral that's growing in those conditions is going to contain more oxygen 18. And then on the flip side, when we have a situation with a lot of rain, that rain tends to be more enriched in oxygen 16. And so that brings more oxygen 16 to the seawater, which is then incorporated into the corals. So more oxygen 18, drier conditions, more oxygen 16, wetter conditions. And when we analyze a coral, we measure each of those layers millimeter by millimeter and track changes in the oxygen 16 and the oxygen 18 through time. And that's exactly what you're seeing here with one of our corals. This one died in the early 1990s, and we have a sample, a transect that runs all the way down the coral skeleton and measures changes in the oxygen 16 and the oxygen 18 through time. And it tracks drier conditions and wetter conditions through time. And turns out people have been doing this for upwards of 30 years now, which gives us a number of sites to work with. And so if we want to track changes in the location of the intertropical convergence zone, it's helpful to have more than one site. And fortunately, we have a lot here. We have something like 8 different coral cores scattered across the Pacific that span the northward and southward extents of the ITCZ. That's more than we have rain gauges in this area. So the sampling resolution we have for our corals is actually better than we have for our precipitation data. So what do these corals tell us when we reconstruct the location of the ITCZ? Well, you can recall, so you can recall our satellite data, which you can picture going here, squiggly, squiggly, over to 1980 with no trends in it. And then we can tack on, or if you could see, you could tack on our coral data, and it goes something like this, something like that. And it might help if I throw a trend line on there, but it doesn't help to see this trend line in this context because, number one, the graph is missing. Number two, the seasonal cycle is swamping your climate signal. It's hard to figure out how the climate is changing over long periods of time, and you have a very strong seasonal signal imposed on top of it. So when we subtract the seasonal signal, you can just look at the trends, and the trends look vaguely something like this. Where again, our satellite data stretches from 1980 to 2020, 2019, and we don't really see any trends. The real picture starts to happen when we include our corals in this record, and we see that the climate showed a southward ITCZ and trended southwards to get to that position. So between about 1950 and about 1980, the ITCZ shifted towards the equator. And that explains why the Marshall Islands were drying over the same period. The islands were high and dry for a longer portion of the year. Less rainfall was reaching there because the ITCZ was further to the south. So by including corals, using corals to supplement our instrumental record, we learned that the ITCZ shifted southward between 1950 and the early 20th century, the rest of the 20th century. That can give us a bit of good news for the Marshall Islands, because it seems like at the very least the ITCZ is not continuing to trend southwards. At the very least it's stabilized. So we know that the rainfall trends aren't going to get worse. In fact, we think they might be getting better, because we know that the ocean conditions that cause the ITCZ to shift towards the equator in the first place are probably going to reverse in the future, in which case the ITCZ might shift back northward and bring more rainfall to the Marshall Islands, which is incredibly valuable in a place that's incredibly freshwater limited. So hopefully I've demonstrated to you that corals can extend our knowledge of tropical climate change, but this is obviously still a work in progress, so we do have some next steps. Now the first of those is that the corals that I've shown you today are these two little green ones right here. They go back to around 1950. We've got all of these corals to work with that go back to the some of them are several thousand years old, several are about 5,000 years old. And so these windows of climate can help us explore how the ITCZ and other aspects of Marshall Islands has changed through time. And we've got an undergraduate in our lab, Maria Snyder, who's been doing a fantastic job on her honors thesis to giving us a first look at these corals and giving us a first look into how the ITCZ's position has changed on long time scales. Our second step is to go back to the Marshall Islands. We have temperature loggers that have been in the water there for over 3 years now. I'm itching to get back and see what data they have. We also have some live corals to sample. And so those can give us better overlap with the instrumental data set, and also give us a better insight into how these corals are responding to the climate change. And finally, just as importantly, we want to share what we've learned with the locals. So this is a brochure that we shared when we were there in 2018. A lot of our fossil corals were in people's backyards. Literally knock on their door and be like, hey, can we sample your lawn ornament, more or less? And so that's kind of hard to explain. And so we would always hand them this brochure to help explain it, which is especially helpful because we didn't speak Marshalese. And so this brochure is presented in both English and Marshalese to try and help explain what we're doing, why they're there. So it's helpful to go back to these places afterwards and explain what we actually did and what we actually learned to just fully complete this cycle of knowledge. And as we take corals from these places, we can return knowledge. And I hope, ultimately, that by giving them this knowledge, we know that the Marshall Islands face an uncertain future, but I hope, ultimately, that this project will give them some information and some tools that they need to anticipate and prepare for that future. So, as I've said before, this project is incredibly collaborative. There are a whole list of people to acknowledge here, including people at the Marshall Islands Marine Resource Authority, people who assisted with our fieldwork, the folks at the Australian Institute of Marine Science who helped us X-ray and measure the density of these corals, the folks here at the UA who have helped us with geochemistry, the people in my lab, including Diane Thompson, and the people who have funded us. And with that, thank you for listening. And I'm happy to answer any questions.
So, is the flooding in the Marshall Islands, does that predominantly happen during the wet season so that when the ITCZ is shifted further south, you're actually getting less flooding? Or is it like big storms like cyclones?
Yeah, I would say it has more to do with storms, and it also has to do with king tide, so where the moon is. And during the highest tides of the year, that's when the sea level is already the highest. So if you take that sea level and it's superimposed like a storm and the storm surge, then that's going to create your flooding. So yeah, I wouldn't say it's necessarily tied to where the ITCZ is.
Can you repeat the question, Anna?
Yeah, so what have I learned about climate change by looking at these corals, right? Yeah. So, yeah, these can give us context to how the climate is changing now. I didn't show this here, but some of the preliminary data from our fossil corals show this kind of iconic, in the climate field, we call it a hockey stick diagram. It's where the temperatures are more or less stable, and they skyrocket towards the present. And if you can plot the chemistry of these corals through time, you see a similar pattern, where you see a very sudden warming and probably a northward shift of the ITCZ between those previous conditions and today's. So we're learning a lot about these corals, about climate change from these corals. We're also starting to learn, I can't really speak to the results of this project yet, but how the corals themselves are responding to climate change. So one of the reasons we work specifically at the Australian Institute of Marine Science is because they're very good at measuring coral health from these coral cores. And so if we understand how the climate has changed through time, and we know how the coral growth is responding to climate change through time, we can get a better idea of how these corals are going to respond to climate change in the future. So yeah, climate change factors into this quite a bit. Yeah.
So in your next steps, there are roughly upwards of 35 to 40 cores in total that need to be done. So I guess the first part is how long does it take to do one? The second part is, if it's a long time, which probably is, which one of those are more, I guess, quintessential? Which one do you actually think are going to give you a better picture faster?
Yeah, that's a really good question. So, yeah, we definitely do prioritize these coral cores. Like, this is well beyond the scope of one Ph.D. It's going to take basically a full career to get through all of these. Because one coral core can take months to analyze and thousands of dollars. So it's not something we do lightly. We definitely do prioritize. And what I didn't show in this figure, in that timeline figure, was that we gauged the priority level of each of these corals. We gauged how long they were, so how long of a record we could get. We also assessed the quality of the record. Are the growth bands regular? Is the coral stopping growing and starting growing? How easy is it going to be to sample? So we take all of these things into account when we figure out which corals we're going to drill next. Yeah, but we also want to target key time intervals. There are key climate transitions, say the transition between the Little Ice Age and today, that we really want to capture, and so we're going to prioritize those corals for sampling. All right, thank you, everybody. Oh yeah.
Is it possible, I brought this up, is it possible to take those slices of the coral and then go back and look at them for contamination?
Well, what kind of contamination are you talking
Well, there's
about?
all kinds out there in the oceans, so I'm concerned about all the plastic flotilla that's in the Pacific. There's all kinds of contaminants. Our coral reefs replay absorbers back so that when you do
Yeah, that's a really good question. Talking about how contaminants such as plastic can impact coral reefs. We're out in the middle of nowhere, and the garbage patch tends to be in a very specific region in the middle of the Pacific. So if I were to show you a map of the Pacific, the garbage patch would tend to be more towards the eastern Pacific and not where these islands were. That's the good news. That being said, it's still near a populated area. There's still plastic going into this region. So the reefs definitely are being affected in the regions that are more impacted. One of the dives we did was right by a landfill off of the main island. You can definitely see those impacts. The corals were sicker or dead, and the reefs were just generally less healthy. Measuring the contaminants in the coral skeleton is a completely different ballgame that I know almost nothing about, but you can measure certain kinds of pollution in the corals. For example, I've seen lead used, and that can be traced back to certain kinds of pollution. And so you can track changes in pollution through time the same way. Regarding plastic in particular, I don't know. That could be an emerging field. Thank you. Thank you for coming.
Great, thanks very much again. And like I said earlier, there's plenty of pamphlets back there for you guys to all take a look at. And please, if you do get a chance and have some time, Emma could really use, basically any of us can use any feedback we get with public speaking. It's incredibly challenging, as you know. So if you've done any public speaking and would like any help, imagine that Emma probably feels the same. So the sheets are in the back, there's some pencils back there. They're not mine, so don't take them. But feel free to fill those out for us. Thanks very much.
Okay. Yeah.